Okay, hello, welcome back. This is the lecture on neural networks. So in many applications, data might be uniformly distributed in input space, but complexity in Y space might be non-uniform. The next slide shows an example where the function has two areas of high complexity and where neural networks excel and standard RBF approaches have a problem. So this is the function we want to model, and here's some data points. So this is X input, this is Y output. And the true function has this property that we need a lot of complexity here in this transition area and also here, but in other areas it looks smooth and boring, let's say. So an RBF, so you might need a lot of them to be able to get this transition right. But then you also, because you don't know a priori where to put them, you probably have to put them also in this area. But there's no data point, so by default, typically RBFs assume 0 output weight, so you typically get this behavior that maybe this transition is modeled well, but in this smooth area with no data, the RBF output will go to 0 and then go up again for this in this region. No, because the data points are only in this transition region. If you take RBFs which are wide, which have a wide S parameter, then you might get the overall trend nicely, like this green curve, but then you are missing out these sharp transitions. So this is this dilemma with the curse of dimensionality. If you assume complexity or high frequency and you don't know where, you have to put your resources everywhere, and then you have this problem. And not only that you need to put resources everywhere, also the interpolation between data might not be really working very well. So in neural networks, one thing is we are using a very special basis function, so-called sigmoidal basis function. So here's how I write it. F of x is the sigmoid applied to a parameter times x plus a constant. And this function sig or sigmoid has a special form. It's 1 divided by 1 plus exponent of minus the input, the argument. So if you have a very large positive input, then this becomes very small, and this expression becomes 1. So to the right, it will assume the value 1 to large positive values. To large negative values, this will become very large. So negative of a very negative large number is a exponent of a very large positive number. So this will approach 0 on the left side. And the complexity of this function will be in the area where the argument is 0. So here's an example how this looks like. So this is sigmoid of 1/2 x minus 25. And then you see this behavior. So here on the left side, it's boring and smooth. Then you have this transition area where this argument here is approximately 0. And then it increases quickly to the value 1. And depending on how you pick these numbers, for example, this one tells you how fast the transition happens, and this one, these numbers together tell you what location this transition happens. You can make this more smooth and put it almost steep and put it in different positions in input space. But the new thing now is, I mean, so first of all, it's just a basis function as before. But the new aspect is that we don't just adapt the parameters which are outside of the basis function, so which come after the basis functions. We are also learning or adapting the parameters which you see over here, which is the v naught and the v, and they're sort of inside of the basis function. There before we apply this nonlinearity. And this allows you to have this flexibility by moving around this basis function. So it's not fixed, it can move around in input space, and it can also to some degree change its shape by being more or less steep. And if you now take several of them, so that's something we did before, we took several basis functions. So now we take several sigmoidal basis functions. We put this w parameter outside of this basis function as before, and then we sum over 1 to h. So h is sort of the old m phi, but I use h here for the number of hidden units. Then we can model pretty complicated functions. For example, here are three sigmoidal basis functions with the parameterized form. So this is 0.2 times sigmoid of minus 1/2 x plus 25/7 x. This one, the blue one, would be sigmoid of 1/2 x minus 25. And the green one is minus 0.5 x minus 22.5. And if you sum all of them together, you get this pretty interesting behavior. So on the left side you have a smooth behavior or boring behavior, then you have this area of sharp transition, and then it's smooth again. And so you can have a local complex activity, and by adapting these parameters, you can move this position, you can make it sharper or deeper or smoother, whatever you want. And so this would also be able to get a good performance in this case, where the sigmoid can be adapted that it can fit this curve quite well and also interpolate here in this central area. This is a little bit related to the idea that we would, I mean, another way of looking at that is we allocate a really large number of sigmoidal basis functions with fixed input parameters, fixed v naught and v, and then just select the ones which are important. And the selection is happening in an adaptation step, but we could also select it in other ways. And this is the approach, for example, used in wavelets or sparse coding. And this approach uses an overcomplete basis, which means you allocate too many basis functions, and you expect that only a very small number of them will have non-zero weights. Yeah, this can be generalized to the case that you have several inputs. So we have a multidimensional input space, and then it looks like this. So xj is now the jth input. We have a weight here from the jth input to the h is the index of the basis function, and we sum here over all inputs, and we multiply the input to the corresponding v parameter and add a constant offset, which is now specific to the hidden unit. We apply the sigmoid, multiply it by the weights, and then sum over all these different sigmoids. So h would be the number of sigmoids, of sigmoidal basis functions. And we have this more interesting input structure, which is just a linear weighted sum of inputs, and the sigmoid is then applied to this input. So this would describe a neural network or a multi-layer perceptron with one hidden layer, which was extremely popular in the around 1990, plus minus. So here are three sigmoids in 2 dimensions. We have x1, x2. We have input-specific weights. But the weights are also basis function specific, and they can, for example, generalize this function, which has a transition here, and then smooth over here, smooth over here, and many other interesting functions. So this is how it looks like in an architecture. So we have m inputs as before, x naught, which is the constant, x1 to xm. And here this is now a real sort of weighted input construct, like in the perceptron. So each of them you can think of being a perceptron, but each of them has a smooth transition from 0 to 1, and not in the perceptron a hard transition from -1 to 1. And also these weights from input to hidden is specific to each hidden node. So each of them is a different sigmoidal function because they all have different parameters. We map them to the space, which I just named Z or Z, from 1 to H. Maybe we add another offset to the output. And then here again, in the last layer, you see a linear system again. So reminds us of the approach with fixed basis functions, where in the output we also have a linear system. So it is exactly the same thing, only that we now don't just pick some basis functions according to some rules or some intuition. We learn these basis functions, and all these parameters, these V parameters, are from input to hidden. So this is now, so if W is a vector, this is a big matrix, and this hides, in fact, a large number of parameters, because each link here is attached with a synaptic weight with a parameter. So so in a way it's also, so in this figure it also performs some form of dimensionality reduction, because any sort of structure or any variation orthogonal to this direction will be ignored. So it also has this implicit dimensionality reduction integrated. So neural networks well suited for large number of inputs, but also small smoothness. So mu I had introduced before in last year, which was a frequency. So we're talking about smoothness. So it can model pretty complex functions with high input dimensions and noisy features, because we have sort of this voting behavior in the beginning that often any individual input doesn't have a huge influence. So there's some really interesting advantages. So also initially people explored also more complex structures also in the 90s, but for most applications people just use the simple structure with one hidden layer. And it was shown that neural networks, even with one hidden layer, only are universal approximators. So any continuous function can be approximated arbitrarily well. Of course, with maybe a large number of neural basis functions, but there was a nice result, nice result that you don't have to go outside of this domain of sigmoidal basis functions. That's sort of sufficient for any interesting problem. Naturally, they can solve the XOR problem. And at the time when it was developed, in the mid-1980s, 1986, was considered the response to the criticism by Minsky and Papert with respect to the limited power of the single perceptron. Now we discussed this XOR problem, which could not be solved by a single neuron, but of course now with a complex system of neurons with hidden layers, the XOR problem can be solved. But the important advantage of neural networks is really that for functions which actually occur in practice, this good approximation can be achieved with a small number of neural basis functions. So if we would need 10 million of them, that would not be very useful. We typically need a small number of hidden units to get a pretty good fit. And they scale well with input, so they work with high-dimensional input space because they have this ability to sort of find appropriate basis functions which are suitable for this particular application. So in the case that the basis functions are really sparse, the neural networks work really well. And this is in a time when people took this curse of dimensionality extremely serious, and they were really impressed by the good modeling power of neural networks, because they all thought this curse of dimensionality makes all these problems impossible to solve. So in regression, as before, the weighted sum of hidden units, they are typically called, the basis functions are called hidden units, is just the output. So we just say f is constant plus weighted sum of the neurons. And so yeah, for the notation, we have m inputs again. H is the number of hidden units. And yeah, maybe we have a single neural network output. Sometimes we have k of them, so we have several outputs. I will show you also in a second how this works. So what I already discussed before, the important is the special form of the basis function, because it fits nicely to problems which need a local area of high complexity and then are smooth and constant outside of this area. And the sigmoid is also called logistic function. We can also compare it to our perceptron. So in the perceptron, we had a weighted input and then applied a sine function to the weighted sum of the inputs. Now, so this would be a single neuron. Now we have weighted inputs again, but we apply this smooth version of this sine function. Also, the sine goes from -1 to 1, the sigmoid goes from 0 to 1. So if we say perceptron, the output is the sine of this expression. Here we now say the y is the sigmoid applied to this weighted sum. So this is how it looks like in 2 dimensions. I always say it's a carpet on a single step. It doesn't have to be axis parallel, it can be sort of diagonal in space. but there's an area where it's 0, so below the step, and then above the step it becomes sort of constant, converges to constant. Yeah, we can also talk about separating hyperplane for a single neuron, and this is typically associated with the point where this expression is 1/2, which means where the weighted input is 0. Yeah, this is we discussed this already. We have m inputs. We have the sigmoidal transfer functions over here. We have the weighted sum of the basis functions. We have the output. So this is, as I said, a very powerful structure already. But also in the 90s there were a number of variants. First of all, how about if we have two classes? So we have one output, and maybe we do the threshold at 1/2. If it's larger than the threshold, we assign it to class 1. If it's lower than the threshold, maybe 1/2, we assign it to class 0. So people put a sigmoidal transfer function also at the output. So we have another sigmoid at the output, which then transforms it to values between 0 and 1. And traditionally, people also worked with problems where you want to assign an input to one out of k classes. For example, in digit recognition, OCR, you have 10 outputs, 0 to 9. But you only use one neural network. I'll show you in a second. And then you have also k outputs, one for every class, so one for every digit. And you just simply apply the sigmoid to the corresponding output for the class. And then typically one decides for the class which has the largest activation. Later on we will also talk about the softmax function, which is more popular in the multi-class problem. And a neural network with at least one hidden layer is called a multi-layer perceptron. So this is the architecture if you have several classes, maybe digits from 0 to 9. Again, we have the inputs. X0 is the constant, then x1 and to xm. Then here we are calculating the hidden layer, so the activation of the hidden neurons as before. But now we don't just have one output, we have k outputs, so one for every digit, for example, which means that between the hidden units and the output units, we also have a whole weight matrix. No? Before this was a vector, and this is now a matrix. This has always been a matrix. So it's also a quite simple extension. We simply have several outputs, but this was also sort of a new idea at the time, because the alternative would be to train a separate neural network for every digit. So you could also train 10 different neural networks separately, but by sharing these connections between input layer and hidden layer, essentially by having the same V matrix for every output, you sort of have a better way of determining the parameters in this input layer, because you simply have more data, more information to train them. And this sort of sharing is sometimes called sharing of information, is often very beneficial. So by using this specific architecture, you often get better results. Then if you learn, so this is the architecture. Now we have to decide how we can fit these parameter matrices in the multi-class case. So I go through this example with the multi-classes. So we have two matrices, W and V. and the cost is the sum over all data points, and then the cost term, which is dependent on the input, xi, and the w and v, and of course also the outputs. So the cost is then for a particular input pattern, xi, is the sum over all outputs, and for each of the outputs we calculate the squared error, or the distance to the power of 2. So this is the prediction of the neural network. This is the y hat is the prediction of the neural network. Y is the actual training target, and we take the difference and take the sum over the square of this distance. But we cannot calculate now these parameters in closed form. So for the multiclass, also for the W naught and for V naught, but even if we have linear outputs where we might be able to fit the W with some least squares made fitting solution, the V's cannot be fitted in this way. I always told you in a lecture on perceptron and also on linear regression, you have, particularly in linear regression, we had this one solution with stochastic gradient descent, pattern-based learning, and another solution was to have this closed form solution. I mean, here, essentially, we don't have the closed form solution. We always have to do stochastic gradient descent. And in a way, that's the whole story, only that the gradient is more complicated because we have this layered structure. So first, let's look at the gradient for a W. So this is from hidden unit H to output unit K, and we're calculating the gradient of the cost function with respect to this parameter. It turns out this gradient can be written in this form. It's -2 times this delta term times this z term. And I is the index of the input pattern, so this is for input pattern I, and k is the index of the output. And h is the index of the hidden unit. And this delta term takes on a particular form. It's a sigmoid, and it's the derivative of the sigmoid with respect to the input. I will show you in a moment how this looks like. Applied to the normal input, and then times the difference of the target minus your prediction. So this is this term, and this is the activation of the corresponding hidden unit. So it looks also like what is called a delta rule, which is a little bit similar to how the gradient in the linear case looks like, or in the perceptron case. Just I have to be careful what these terms now mean. And this delta is called the backpropagated error signal, and this whole learning approach is called error backpropagation. And delta ik, so I is the pattern, k is the output node k, so it sort of belongs to the output node k. And if we do stochastic gradient descent learning, we go through all data points, all patterns, all outputs, all hidden units, and adapt the weight from hidden unit H to output unit K. It's the old weight plus learning rate times this delta term, delta ik, times ZIH. So this looks similar to adaptation in the linear perceptron or the perceptron, and it will continue to look that, only that essentially this delta becomes more complex, the backpropagated error signal. Oh yeah, so here we don't have the sigmoid, but the derivative of the sigmoid with respect to the argument. And if you apply the formulas for taking derivatives, you have to take here, this term to the square, the denominator, and then here you have to multiply it with the derivative of this term, which is the same, because the exponent, if you apply the gradient, it stays the exponent. And this can now be written as a sigmoid of the input times 1 minus the sigmoid of the input. And thus this delta ik can also be written as y hat of ik times 1 minus y hat of ik times the difference. And this is most sensitive if y hat is approximately 1/2, because if it's more like 1, then this becomes 0, and if it's 0, then this term becomes 0. But technically, although it looks maybe complicated, it's just, again, the calculation of the gradient. But we don't only have the weights from the hidden to the output units, we also have the weights from the input to the hidden units, and this turns out to have the same form. So look down here. But this delta term is sort of propagated through the network backwards. That's why it's called backpropagation. But this gradient with respect of the cost respect to V, H, J, so this is jth input to the hidden unit H. So formally it assumes the same form, so it's -2 times this delta function times here now the input to this layer, so which is xij. And the backpropagated error now looks like this. It's again the derivative of the sigmoid applied to the input to this sigmoid. Now we sum over all output units, and we take the delta, which we have calculated before, for this output unit k, for the input pattern I, and multiply it by the weight vector wkh. So we sum over these expressions. And then with this identity we just learned about, we can write this as ZIH times 1 minus ZIH times the sum. So this is the formula, and you can try at home to derive this formula as an exercise. It's a little bit bookkeeping with all the indices. But then the nice thing is that after we did this, the adaptation rule so it has the same functional form as before. So it's V, H, J. It's the old one plus eta, this delta term I, H, and Xij. And you can go even several layers. If you have a neural network with several hidden layers, you only have to apply this rule, and you get the gradient by this rule. Yeah, so by pattern learning, we iterate over all training patterns. If xi is the training data point at iteration t, we apply xi and calculate zi and yi. So this is the, I guess it should be the yi hat. Correct this. And then you sort of see what kind of errors the prediction generates at the outputs. You generate these delta IH and delta IK, and then you adapt the output weights for all H's, of course, and all K's, So it's the old weight plus eta times delta term times z term. And for the v, it assumes the same form, only that here it's eta times delta times xij. These propagation rules in a way are local, and you can apply it layer by layer, so it can also propagate to several layers, which is considered to be a biological plausible type of operation. Yeah, if we go back to our analysis on complexity, of course it works well in cases of 2, 3, and 4. So it works well in blessing of dimensionality with low input dimension but high complexity. And of course it also works well if the inputs are high but the function has low complexity. But in particular, of course, in case 1, it would in general also have a problem unless we have a case 1a, which means that we only we can model the function with a sparse basis. So a lot of weights on the basis are 0, and the neural network, by this nonlinear adaptation, has a chance of finding the important bases, which are non-zero. In particular, in the beginning, people were worried a lot about overfitting. Now you sort of learn the noise instead of the structure in the problem. In particular, since we have a huge number of parameters between the input layer and the hidden layer. And so we have to do something about it, but the solutions are partially quite simple, as we will see in a second. And either we use regularization or stop training, or we do both. So regularization is pretty close to what we already know about. So in addition to the cost function, which is a data term, we also put penalty on large weights as before. And we have regularization parameters, maybe different ones, lambda 1, lambda 2, for the different types of weights. And before we had one sum here, now we have two sums because this is a matrix. So this is output and hidden, this is hidden and input. But essentially it's the same idea as before. We penalize large weights, positive or negative. And this can be also be absorbed in the learning process, in the stochastic gradient descent, by adding this term for w, lambda 1 divided by n times w kh, or in the second case, lambda 2 divided by n times vhj. And since this term, if this term has no impulse from this term will take care that weights become closer and closer to 0. This process is sometimes also called weight decay, because large weights will be encouraged to become 0, in particular if they're not used full for the adaptation, if they don't see an error signal. So here's an artificial example. It's data for two classes, so red and green circles, which are generated. The classes overlap. The optimal separating boundary is shown dashed, and a neural network without regularization shows overfitting, which is the continuous line. So we have two classes, green and red. This is the best possible classification boundary, so it has a pretty strange shape. So we need high frequencies. So we even have islands of data, but still the true separating function is over here. So these are sort of noisy data points. And this also illustrates an important issue. In some case, I mean, before we said, okay, we need to solve XOR, we need high bandwidth or a lot of basis functions. But it's not always the goal to separate the classes because the classes might overlap. So for example, if you want to classify somebody as a promising customer and you look at whatever, how expensive the car is that this person is driving, then it gives you some indication if this is a good customer or not, but it's not a deterministic rule. So you can also say if he has an expensive car with some probability, this is a good customer. And in machine learning, this is called overlapping classes, that you cannot really, and you should not really try to separate the classes because we have these probabilities of being in one class and the other class. So you see this here quite expressed. So here, for example, are data points which are labeled with red, or they're in the green region, and here green data points in the red region. And this is what the neural network solution was. So it's a pretty discontinuous looking boundary, and it sort of is not doing such a bad job. It sort of tries to separate the classes as good as possible, but in doing that, it also introduced like these regions, assigned them to the green class, although they don't really belong to the green class. Its area still belongs to the red class. I mean, the data points belong to the green class, but it's just noisy data. The real data is the red region, and here's the opposite. And here you see the numbers. So the training error is 0.1, quite nice, small. The test error is 0.259, and the Bayesian error is the best possible error. So if you would know this true boundaries, then you would get 0.21 error. And this neural network had 10 hidden units and no weight decay. So obviously it was overfitting to some degree, although it was not necessarily doing such a terrible job. Then in the experiments, regularization was applied with regularization parameter 0.2. And then we get these results. So it sort of looks much nicer. We don't have this unsmooth behavior. It's a smooth separating hyperplane here and here, or hyperspace. And of course, it's not perfect, in particular in areas where there's no data. It didn't do this mysterious like assignment of classes in this red region to the green region and the other way around. But what is important, what we are seeing here, is that the training error is going up, no? Because we don't just minimize the training error, we minimize the training error plus some terms which penalize overfitting. So here it was 0.1, now it's 0.16. But as a reward, the test error became better. Here it was 0.259, here it's 0.223. So we are rewarded for our penalty, and it's getting closer to the base error, the best possible error. Yeah, we are always talking about this lambda, this regularization parameter, but I haven't really told you how to pick it. And we have this lecture on model selection where we go in more detail on this issue. But here's already some idea. So essentially, you look at a data set which is not the test data set, although it's called test error here, and look at this behavior. So we have this lambda, so this is a very small, this lambda equals 0, and then it increases. And if we don't have any lambda, then the test error is not the training error. The test error is pretty large and can also vary a lot. So the solution is sort of unstable. No? So I think this is simply a different split between training data and test data. And then with a little bit regularization, you get this instability out of the system. and and also your test error becomes smaller. And then if you increase further, your test error gets smaller and smaller. But then you shouldn't overdo it. If you put your lambda, this weight decay term, to a really large number, then you see what is sometimes called underfitting, or you don't allow your network to really explore the complexity of the data, and then the performance gets worse again. And this is a typical curve. No? You have overfitting if your lambda is too small, if underfitting if your lambda is too big. And also you should be in this area, but it doesn't really matter if you're a little bit too large or too small. That's also a message. No? You don't have to pick the absolutely best realization parameter. It should be approximately a good value. Yeah, there are some variations on this basic architecture. We already discussed a few. Here are a few more. So you can use more than one hidden layer. And that's, of course, very popular today and these years. And that goes in the direction of deep learning. And it turns out you can really gain a lot in some problems by using many hidden layers. In the 90s, maybe one or two. Now sometimes they're using hundreds. Then you don't have to use a sigmoidal transfer function. You can also use, for example, the tangent hyperbolicus or tanh, which goes as a smooth function between -1 and 1, where the sigmoid is between 0 and 1. If you use a tanh, then sometimes you also switch your target to -1 and 1 instead of 0 and 1. Or people use often the tanh in the hidden layer, but then in the output layer, they use the sigmoidal function. So the tanh really looks like the sigmoid, only that it's goes between -1 and 1, and goes to 0 at 0, which is sometimes you like to have. Yeah, then relatively early on, people found that applying the squared error after the last sigmoid is maybe not a good idea. And they used, and it's still used today, if you look at books on deep learning, the so-called cross-entropy cost function. So it looks a little bit strange, and we will discuss later why it has this particular form. So here we see the sum over all the outputs, and here's the target, so yik, and then here's the log of your prediction. So it's not the prediction, but the logarithm of your prediction. So this is after applying the sigmoid, so this is between 0 and 1. Plus 1 minus the target times log 1 minus your prediction. And this looks a little bit strange, but you should realize that y is either 0 or 1. So if it's 0, then this term drops out, and you only have this term. And if it's 1, this term drops out, and you only have this term. And if we look at the, for example, the gradient of the with respect to w, now we could always write it as -2 delta z. In this cross entropy case, zik is simply the difference between target and prediction. So before it was this much more complicated expression. So the issue here is that this term becomes 0 not only if you're correct, but also if you're really incorrect. because either so one of these terms becomes 0, and then the gradient information is lost. And that's the main reason why people don't use the squared error on the sigmoid of the outputs for classification anymore. They use the cross entropy cost function, which gives you better performance in the training process. Yeah, the activation of the output for several classes is the exponent of f. So before the nonlinearity divided by the sum over the classes exponent of f. So this automatically gives you the correct correct normalization, because now the sum over, if you sum this over all classes, it will sum to 1, and it's positive, it's non-negative, so you can interpret this as a probability if you use the softmax output activation. Yeah, if you apply this to an input pattern, then you have the log of the sum of the exponent of the fik. So you sum over all classes, and then you have the second term, but for the multi-class, you have only one here. So this is only active for the class which is the correct class at the output, because there this term is 1, and for all other classes this term is 0. So for the outputs which are not currently the correct output class, you only have this term, and for the one which is the correct output class, you have this term here plus this term. So now we discussed weight decay and another cost function, the cross entropy cost function. But there's an even simpler way of doing regularization, so avoiding overfitting, and that's called stopped training. So it's probably better to look at the figure. So this is what you often observe when you are training a neural network. And since this takes some time, you typically monitor your training progress. So this is the number of epochs, and one epoch just means you went through all your training data once. So you have to, since you're using stochastic gradient descent, you have to look at every data point several times. So one epoch means every data point has been visited. And then you observe, look at your training error, so what is the cost function on your training data, and then you see a nice decrease. So the longer your training, the better the training error. It always goes down, down. But if you then leave out some data, which you don't use in training, but you are using it for testing, so forget about the validation data here for a second. Then you see the following behavior. Initially, typically the error is a bit larger than the training error on average. And then you see also a nice decrease in the test error, which is nice and nice and nice. But then at some point, although the training error goes down, the test error starts going up. And this is this region where overfitting occurs, where you're sort of learning the noise, which sometimes it's called. And of course you then could say, okay, let me take the model which was there after 5 epochs, because that gives you a better test set performance than after 10 epochs. And since you are essentially interrupting the training process by doing that, this is called stopped training. So that's what I say. It's really extremely simple. You don't have to do don't have to add anything to your cost function. You just do training. But you're just monitoring these two things, the training error and the test error. And if you see that the test error goes up, you say, okay, this is the model I will pick. Now, typically, you would go a little bit further to really confirm that it's going up, and then say, oh, let me go back to the model I had after 5 epochs, and that's it. So that's a very nice way of regularization, also invented in the neural network community. But it's very powerful and used all the way, everywhere today. So this is why you can also think of this as weight regularization. So here are two weights, W1, W2. Here's the, let's say, the optimum. And then during learning, you're going into the direction of the optimum. And instead of going all the way down, you're stopping before you're reaching the optimum. Because we don't have regularization, this would overfit. We showed as we looked at in the example. And here you also see that it almost acts as a weight decay parameter, no? Because W1 is still smaller than in the optimum, W2, and W1 is also smaller than in the optimum. So that's why you see it's sort of a similar behavior than with weight decay if you do stopped training. Yeah, there's not just lambda, there's also eta, and we haven't really discussed this a lot so far. Of course, eta must also be a good parameter, because if you pick it too small, you can wait forever until it converges, and if you pick it too large, the whole learning process can become unstable. And yeah, fortunately, there are nowadays procedures where this eta is tuned automatically, so you don't have to do it by trial and error. One which seems to be very popular these days is called ADAM. So if you look at deep learning books or literature, you often find it. It stands for adaptive moment estimation. But here's the illustration. So if your eta, your learning rate, is constant and it's much smaller than the optimum, then it will always go down. So now we're looking at the training error again. It has this is the cost function. This is some weight space. So it will go down and go down and go down, and but it will take a really long time to hit the optimum. If you're lucky and you know the optimum eta, and if this has this sort of quadratic behavior, then you can reach the optimum in one step. This is done if you use quasi-Newton methods or Newton methods for optimization, and if this is really a quadratic function, then this can be done. Essentially, it means the same thing as we have a closed form solution for the optimum. It's sort of equivalent. If you are a little bit too large, you see an unstable behavior. So if you look at the weights, it will switch forth and back all the time, but eventually it might settle into the optimum. And if your eta is really too large, then the whole learning procedure can even become unstable. So it is important to pick the right eta. You don't want to wait forever, and you don't want to have unstable behavior. And fortunately, it can be automated by using, for example, this Adam procedure, which takes this load out of you. But you see, I get a feel that there's a lot of engineering going on, and that was criticized in the 90s. The theoreticians didn't like it. That's why we moved away in the 90s from neural networks to other things. But now it's all back. So deep learning has a lot to do with good engineering because the performance is simply so overwhelmingly good. There's another problem with neural networks, and that's the problem of local optima. So the thing is, if you, for example, in regression or other linear approaches, there's really only one optimum. I mean, if you use regularization, there's only one optimum. So it's just a matter of finding it. If you have something as complicated as a multi-layer perceptron, as a neural network, there are several optima. So here's an example. The red curve is the cost function, and this would be the global optimum, so the lowest value of the cost function. But if you're doing gradient-based learning, you might end up in this local optimum, which locally is an optimum, and would say, okay, this is my solution, and you don't know that there is even a better solution over here. Yeah, that's another reason why people thought neural networks can never work in the 90s. It turns out that this is not such a severe problem after all. Nowadays in deep learning, people think there might be a lot of local optima, but they are all very good optima. You should avoid really trivial bad optima, but if you do some smart things, you can find a very good optimum. Because people, I mean, sometimes learning takes like days or weeks, and if you would have to try a lot of different things to avoid this problem of local optima, it would take forever. So this is how it looks like maybe in 2 dimensions. So W1, W2, and you start training somewhere, and your weights move and move and move. Find a local optimum. I'm happy, I'm done. All the gradients are 0. But you already see in 2 dimension it might be, you might already have a good chance to avoid this local optima and get into the global optima. Yeah, the thing is that the algorithm doesn't know that this is local because all the gradients are 0, which is a condition for an optimum. In any direction this is moving by a small step, it looks like it's getting worse. And of course, how should it know that if you take a really big step, there's a better solution? That's another reason why people thought neural networks can never work. So one thing is already stochastic gradient descent, which has fewer problems with local optima than if you would calculate the true gradient. And that's shown over here. So by this pattern learning, we have the trend of moving in the right direction. But since we are looking always at one pattern at a time, we bring in stochasticity in the learning process. And just by this stochasticity, optimization might avoid this local optima and jump out of it even, and eventually settle into the global optimum. So stochastic gradient descent is not a problem, it's a feature, it's a beneficial thing. It's not just faster than batch learning, it also has a better chance of avoiding local optima. There are also other ways. One is restart. So you simply start with different initial random numbers and see if what the performance is, and then you pick the best one. Maybe 20 different you train with 20 different initial weight conditions, and then see what the performance is, and take the best one. Or there's an even better idea, and it is called a committee. So you do the same thing. You train maybe 20 neural networks with different initial conditions, and then you don't just pick the best of them. You average the responses. or you take a majority vote. So if 10 of them or 12 of them say it's class 1 and 8 of them say it's class 0, then you take class 1, you do a majority vote. And this idea of using a committee of neural networks instead of a single one is also quite powerful and works often very well. And sometimes if you report performance or if you read a paper, then they sometimes discuss the best single model and then the best committee, because it's sort of unfair to compare a single solution to committee, because committee are typically adding something, but it's just an additional step. So it's you also want to see the performance if you're not using a committee. One a little bit more systematic approach is called bagging. It stands for bootstrap aggregating. So it's a committee as before, so and you average the predictions, but you also disturb the data for every committee member. So you add a little bit more noise even to each training process. And this uses a bootstrap, what is called a bootstrap sample. And a bootstrap is simple to explain. So let's say we have only 5 data points, so 1 to 5. And then in a bootstrap process, let's say we consider this first one here, we randomly pick one of the original training data points and put them in the new set, the new bag. It's called bag. So first we put but each time we do it randomly. So we pick 1, and then 2, and then we pick two again, and then maybe 4, maybe 5. And each time, since we do this randomly, we will get a slightly different data sets. No? So here we have 2 times the 2, but the 3 is missing. Here we have 2 times the 1, 4 is missing, and so on. So and this is sort of called a generation of bootstrap samples. And then if we train our neural network or our model on these bootstrap samples and average them, that's called bagging, and it also works quite well. And there's one procedure when you apply to decision trees and go to even more complicated ways of disturbing the individual models. It's called random forest. So it's probably covered in some other lectures, maybe on KDD or in the statistics lectures. And it's amazingly powerful, works very well. And before deep neural networks, it was winning a lot of these competitions. So Kaggle is some organization which organizes competitions, sometimes for companies, if they give out data sets, and then the whole world tries to get the best results. And before deep learning, often random forests provide the winning solution. So it is a very powerful approach. And if you're interested, particular, maybe want to find a company or something, you should look at random forests. So neural networks are very powerful and show excellent performance. The training procedures can be complex and slow. Of course, with modern computers, it's faster than in '86 when they invented this, when it took like weeks to even train a simple problem. But one can also say that a neural network really learns something. At least some people argue. There's optimal representation of the data in the hidden layer. There's really some effort there. You can really call it learning. Whereas some people say if you just adapt the output weights in a RBF network, that's not really learning. But I think it's a matter of opinion. But even if the training takes a while, the prediction is very fast, because these operations, in particular these vector matrix multiplications, can be efficiently implemented, also using GPU computers. But in general, predictions can be quite fast if the network is not too huge. Then, as we discussed, neural networks are universal approximators and have excellent approximation properties. Yeah, so in contrast to basis function, the training of the neural network tries to find the right set of basis functions, and it might be a small set, no, so we don't have run into this exponential problem. But the disadvantage is that it's sometimes of an art, so theory people don't necessarily like it very much. A lot of hyperparameters have to be tuned. You need to be an experienced person to some degree. You have to tune the number of hidden units, which we haven't discussed. No? So a typical number in the 90s was maybe 20 hidden units, but why not 22 or 30 or 40? So you often try out different architectures, which is time consuming. The learning rate has to be fixed or automatically tuned. You have to think about regularization parameters. So it becomes complex or complicated without any question. Although not all problems can be formulated as a neural network learning problem, surprisingly many can. Also, I mean, this engineering flavor, you can think of a disadvantage, but you can also think of it as an advantage of having developing an intuition of how a neural network works. Also gives you a lot of flexibility and how exactly to apply a neural network. And sometimes you can formulate a problem very easily as a neural network training problem. And if you would do it by the theoretical approach, you would end up with very complicated equations. So you have also a very powerful system at your hands. A certain disadvantage is that this issue is local optima, but there are some solutions, multiple runs, committee machines, and in the deep learning, this problem seems to go away to some degree. And so I told you a little bit how backpropagation works, how the gradients are calculated, and in the 90s there was a lot of calculation of gradients going on. Fortunately nowadays in tools like Theano, TensorFlow, Keras, Python, PyTorch, and others, this calculation of these gradients is done automatically for you. So people design incredibly complicated neural architectures, and we will learn a bit about them. And if you would need to calculate the gradients by hand, it would be impossible. You would simply do too many mistakes. But there is this algebraic way of calculating a symbolic differentiation, which gives you the gradient automatically. You specify the architecture, and the software calculates the gradient for you. And this works. I mean, takes up. Of course, it works. It doesn't do any mistakes, and it takes out off this load of your shoulders to calculate the gradients, which would be impossible. And I mean, you would just do too many errors without this automatic symbolic differentiation. So that was a huge practical asset when this was developed. Yeah, finally, a comment on approximation accuracy of neural networks. We have had some discussions in the last lecture. So here's a paper from Andrew Barron, where, I mean, it goes in it's a very similar direction to our discussion before, but there's some specialties in the neural network case. In particular, I mean, we introduced the smoothness parameter. He introduces the inverse of the smoothness, the complexity, and he defines it in this way. So f is the function, and f tilde is the Fourier transformation of the function, and w is the frequency. So this means I calculate the Fourier transformation, take the magnitude of the coefficients, multiply them by the magnitude of the frequency, and take the integral. So essentially what this means is look at the high frequency components, integrate them, and if you're really high, then you even put more emphasis on the high frequencies. So this says, so CF tells you something about how smooth the function is. So if CF is high, it's a very unsmooth function. If it's low, it's a very smooth function. And in our old notation, maybe we would say the smoothness is 1 over this complexity measure. The task is to approximate a function from this class of functions with a given smoothness. So we use now M with a model F with parameters W as before. Input dimension is M, and we are considering H hidden units, so H neurons in a neural network with a single hidden layer. And as before, we define the approximation error as a distance between the function and the parameterized function, our model, and it's the integral of the difference squared over the unit ball divided by the volume of the unit ball. So it's the average distance. And Baron, so he did this work, showed that for every f in this, for which this CF is finite, or notation would be M, there's a neural network with one hidden layer such that for neural networks, the distance between this function f and the best one out of our model class is smaller than 4 divided by hm squared. So h is the number of hidden units and m is the smoothness. So the distance is smaller if the function in the target class is smooth and if you increase the number of hidden units. But m doesn't, the input dimension doesn't even occur in this equation. So he could show that this distance measure is independent of the number of inputs, whereas before we had this exponential influence of the number of inputs. Or we can also solve this for h and say the number of hidden units is on the order of 4 divided by epsilon, which is the approximation error we are willing to tolerate, times m squared. So it goes down if the function becomes more smooth. And before, remember, with fixed basis functions, the number of basis functions was the order of 1 divided by epsilon to the power of m divided by m. And if this looks a little bit abstract, I put in 0.1 for epsilon. Then in the first case for the neural network, h is 40, whatever, it doesn't mean much, order of 40 divided by m squared, so it really goes down with the smoothness of your target function class, and m doesn't occur here, whereas if you use fixed basis functions, it's order of 10 to the power of m divided by m, so m, the input dimension, occurs pretty prominently here, and m, yeah, smoothness also gains here, but input dimension can kill you really. So here are some sources if you want to read up. Before I also had this other reference of Porteous article, which is a little bit more modern. But I thought this analysis of Baron was quite meaningful and tells you a lot about what's really going on with neural networks, at least in my understanding. So in the review before this lecture, I missed out, I think, on the last slide, and we can quickly go through this because I think it's an important slide. So here are the target classes. Here's the models to use. So this is also a little bit of a review, but now we have a little bit more insight into another class here. So the first one was the curse. So M is large, big M is large, small m is small. so not much smoothness, but high dimensions, and in a way nobody can really do anything here. All the models fail, and this is what people thought would kill everything, not just neural networks, but don't try anything in high dimension, it will never work. You have the curse of dimensionality. But then, if you look closer, there's this case blessing of dimensionality, where m is small, but I mean big M is small, but small m is large. Is small as well. So m divided by m is still reasonable. So which means we have low dimensions, but maybe high complexity. And here this transformation in the higher dimensional space by basis function works. So that's why I call it blessing of dimensionality. So linear models don't work because they cannot deal with the complexity. Neighborhood models like nearest neighbors can work. Fixed basis functions work. Neural networks work. Deep learning works, and kernels work. Then there's the case that M is large, so high dimension, but the smoothness is also large, so M divided by M is reasonable, which is also often the case. So linear models like this, like high dimensions, but more or less linear behavior. Neighborhood functions might have a problem here because of the high dimensionality. Fixed basis function, if you just pick very smooth basis functions, can work well. Neural networks work well, deep learning works well, kernel works well. Simple, of course, everything is easy. Small dimensions, large smoothness. And now we talked about this, the sparse basis, which the neural networks can find. So neural networks still don't perform very well. So we are now talking about high dimension, high complexity, but sparse basis. So the complexity is limited in some sense. Linear system cannot exploit it, neighborhood cannot exploit this, fixed basis functions cannot exploit this, but neural networks, as we discussed, sort of can, by the adaptation process, find these the appropriate basis, which is non-zero weights, has non-zero weights. Deep learning has not the problem. Kernels don't really work in this necessarily very well. Then we have the issue that input data is on the manifold. We'll come to this back later. Linear system cannot exploit this. Neighborhood systems cannot exploit it unless you do some smart preprocessing. So the DR stands for dimensionality reduction as a preprocessing step. Fixed basis function, same thing. Essentially, they cannot deal with it unless you do some smart preprocessing. Neural networks are very good at that. Deep learning is even better. And kernels, because they put the resources where the training data is, can also exploit this manifold distribution of the input data. And the last one, which we'll discuss next time when we discuss deep learning, is the composable class of target functions. Okay, I just wanted to also review this because I think it's important to understand neural networks and deep learning. So, yeah, to wrap up deep neural networks, they were sort of popular they were invented in 1986, so maybe were popular, I would say, until the end of the 90s. Some people say earlier, people lost interest. I think I wrote my last neural network paper in around 2000. And even then they were quite powerful, but because of all these engineering tricks, the community didn't have too much respect from other fields, although I always say there were some really good people in the other fields, in statistics, in control, adaptive control, who very well recognized the power of neural networks. So there were even like really important people who understood that this is something. And the enthusiasm didn't go down because the performance was not good. It was mostly because, we didn't have recognition, and also people wanted to do things which have a better theoretical grounding, where you don't have this issue with local optima, for example. So where things seem to be a little bit more scientific and less engineering. But we will continue next time also in the trip towards deep learning. And at some point we will discuss kernel systems, which is what was between neural networks of the 90s and now the deep learning area. What people were using a lot are these kernel-based approaches and systems. Okay, so yeah, thank you very much for your attention, and yeah, I talk to you next time for the next lecture on deep learning.